All right, so welcome to our last May class here in Physics 208. And today we're going to continue talking about Schrodinger's equation, but we're going to start turning our attention to atoms and atomic structure and how that plays a role in, or how that's tied to Schrodinger's equation and how we can use Schrodinger's equation to determine the most likely location of, say, an electron in an atom. And we'll start kind of setting the table for atomic structure, looking at why the periodic table is organized the way it is. We'll start addressing some of the things that you learned in chemistry, like orbitals and all that. And so that's where we're heading. We're going to start looking in the atom, which then, of course, is going to make us start looking at the nucleus, and but that's the next couple of weeks here. But anyway, so that's my plan today. But before I do that, any questions about the homework or anything else we've been talking about?
If nobody has any homework questions, I actually have a question about the upcoming content, if you can answer it before we get into it.
Sure.
Will we be going over like what makes rare earth elements so unusual in their properties?
No.
No? Okay.
No. What we're going to do, as opposed to, in a chemistry class, we're going to talk kind of bigger picture. We're going to talk more the why they get structured the way they are in a kind of more macroscopic view, right? As opposed to, and what I mean by macroscopic, I don't mean like, but just like big picture, right? So we're going to be looking at that more. We're not going to break down and look at, okay, so what about, noble gases? Why are they different than, whatever else? So no, Jake, we are not going to be talking about the rare earth metals and why they do what they do. So.
Okay. I was just curious because in the chemistry class that we took last, I remember we went over orbitals and we went over like the d orbital and how only rare earth elements have that, and that's why it gives them freaky properties. But then, like, I felt a little bit disappointed because we didn't get an answer as to like why that happened. But yeah,
Yeah, Sean would never tell us.
yeah.
What a jerk. Now, so I will definitely talk about like what it means when you're in the PSDF, all those different orbitals. But really the whys behind it, at least the way we're going to be looking at it, it's all coming from Schrodinger's equation. And just how the quantum numbers can relate to each other. And you may have just caught I said quantum numbers. We're going to see that there's quite a few quantum numbers, more so than just the one we've talked about so far. But to really go into that kind of detail, we don't have the math for it, first of all. And then, yeah, so we're just, and we don't have the time, honestly. There are classes where you get into all this stuff, like you've heard of PChem, physical chemistry. Physical chemistry classes really start getting into that, and I would imagine that, like, if you ended up being a chemistry major or even go to grad school in chemistry, you really do that deep dive into there. But no, we're not going to go that deep. So sorry to disappoint you, but there it is. But I see while I was chatting about that, Ralph asked to look at number 26 from chapter 6, and Bradley agreed with that. So let me pull up the book here and we will go take a look at that. Make sure I share the right screen here. Okay, so number 26 here, it says the Balmer series for hydrogen was discovered before either the Lyman or the Paschen series. And the question is, why? All right, well, to answer this, we should probably know what those things are, the Balmer, Lyman, and Paschen series. And I don't think I talked about these. And it wasn't, I intentionally didn't talk about them. It just, they kind of never came up. But did you guys figure out what they are? Like, what are these different series? What do they represent?
I'm pretty sure they calculate wavelength
Okay, and they
of
do, yeah.
hydrogen atoms.
So they are looking at wavelengths of photons that are coming from hydrogen atoms. So the Balmer series is one set of them. The Lyman series is another set. The Paschen series is yet another set of them. And so they're grouped together for a very specific reason. You know, when I say like they're grouped, like the Balmer series, they're together because they share something in common, as opposed to the Lyman or the Paschen. Okay, so it's all about wavelengths that we're getting. So let's just kind of backtrack. When we talk about a photon and the photon comes off with a specific wavelength, what determines that wavelength?
It's like the amount of levels that the electron travels, right?
Okay, so it's definitely number of levels that an electron jumps. And so really what's causing the different wavelength is the change in energy. We saw that energy was equal to, of a photon, was equal to h times f. So f was your frequency, but frequency, wavelength, they go together, right? So when we send off this photon and I hand you this energy, depending upon how much energy is in this, determines the frequency of this photon, which also determines the wavelength of this photon. Okay, so for all of these, we're looking at energy jumps. And we already saw that the energy was quantized. Do you guys remember how there was a sort of like a baseline energy, and then we multiplied it by n squared for that quantum number? So you get one of those, or four of them, or nine of them. So when we're jumping from level to level, we are sending out a different amount of energy. So I'm gonna draw a picture here on the whiteboard. Just pull it up here. All right, so let's think about different energy levels. And I'm gonna draw them like ladders, rungs on a ladder. Okay, so this is gonna be n equal 1. And then let me go down a little bit further here. So this is n equal 2. So then this is n equal 3. And this is n equal 4. And we'll put one more on here just for good measure. N equal 5. And basically you can think that this axis has our energy. So these are our energy levels, which means that there is a 0 somewhere. And let's just say that that 0 is here. Okay. So don't worry about the horizontal axis. It doesn't actually represent anything. I want to show the ladder. So basically, just think about it as this distance right here, this gap. That's our, I'm going to call that E naught. That's just our basic level of energy. So n equals 2 has, or so if this is E naught, this is 4 E naught, this is 9 E naught, 16 E naught, 25 E naught. So hopefully you kind of remember that there's this times n squared. That's why they get separated by more and more as we go. But anyway, so think about what happens when we drop or change our energy levels. So for example, we could have a drop from say 3 to 1. So this one, its change in energy is going to be 8 E naught, because we went from 9 to 1, which then is going to lead to a corresponding frequency. So the frequency is going to be that 8 E naught divided by H, not H slash, just H. Sorry about that. Right, so that would be that one. Now, if we change to do a different drop, like let's say we go from 5 to 2, that one, its change in energy is going to be 21 E naught. So its frequency is going to be 21 E naught over H. So each one of these drops is going to lead to a different frequency, depending upon what that energy gap is as it's dropping from one level to another. And it doesn't have to be a drop of just one, like it can be from like n equal 5 to n equal 4, but you can go from n equal 5 all the way down to n equal 1 all at once, releasing a much more energetic photon, which then is a photon with greater frequency or smaller wavelength. Okay, so that's what's going on here. Now, in terms of these different series, the Balmer and the Passion and the Lyman, they all correspond to different drops or different jumps in this on this ladder. And what I'm going to do here, let's see if I can find it. I'm going back to, oh, there it is. There's a picture in the book here for you, so you can see the drops here. Let me switch it back. One second here. Okay, so here are the different series. So the Lyman series are the ones that all drop back to 1. So these are all the wavelengths or all the frequencies that you get when we drop to ground state. So from 2 to 1, 3 to 1, 4 to 1, 5 to 1, 6 to 1, right, whatever. So that's those wavelengths. The Balmer are all the ones where we drop to 2. And then the Passion are all the ones where we drop to 3. Now there may be, and I'm not really sure, but there may be names for the ones that drop to 4 and the ones that drop to 5 and so on. But I've never heard them, so I'd be willing to bet they're named, but they're not very common. Okay, so anyway, these are the different guys. So the question is, why were these guys found first? All right, well, any ideas? Any ideas why you might have seen those first?
My only idea is you can see 4 spectral lines with hydrogen with the naked eye.
Uh-huh.
And back then they didn't have, greater technology to see more.
Yep.
That's
And
but I
that's
can't
exactly it.
I can't figure out how to relate it though.
So these are the ones that are visible. Those are actually visible to the naked eye. Those are the spectral lines that you're talking about, Bradley. Now, obviously not all of them, because there's, more than 4. But the visible ones are in here. Like, for example, let's just look at, let's do the calculation and let's see if we can figure out what wavelength we would get for one of these. So let's look at the state of going from n equal 3 to n equal 2. All right, so that's those two energies. So what's the energy change? Well, we take the 1.51 and the 3.40. And the difference between those is what, 2.89? No, 1.89 electron volts. I was just looking for my tools for the whiteboard, and then I'm like, wait, I'm not in the whiteboard. Okay, so 1.89 electron volts. Okay, so that's the energy drop. Now we know that this is going to equal HF. And let's just go ahead and go to wavelength. Do you remember how frequency and wavelength are related?
C
Lambda.
equals lambda times, it's mu stands for frequency, or no?
F would
F,
use that,
yeah.
but yeah. So lambda times F is equal to the speed. So in this case, the speed of light is c. So F is equal to c over lambda. So lambda is going to equal hc over 1.89 electron volts. All right, so I'm going to grab, I got a physics book here that's got all my values of all these things in here, because I do not have these numbers memorized by any stretch of the imagination. That's false. I have C memorized. Do you like how I say that with pride? I know what C is. Oh. All right. So H, Planck's constant, and I'll do it in electron volts. It's 4.136 times 10 to the minus 15 electron volts per second. Now we're going to multiply that by 3 times 10 to the 8th meters per second squared. And then we're going to divide. Something was wrong with my units. Oh, first of all, it's not meters per second squared, it's meters per second. Oh, that's because these are electron volts times seconds. Sorry. Okay. Anyway, and then we're going to divide by the 1.89 electron volts. All right, so this should just leave us meters. So let me see what I get here real quick. So 4.136 to the minus 15 times 3 times 10 to the 8th divided by 1.89. And I get 6.565 times 10 to the minus 367 to the minus 7, which is 656 nanometers. What color is that?
Red.
Yeah, it's definitely on the red end, right? So it's going to be kind of a reddish color. Has Kathy shown you guys the gases and the spectral lines with the gas tubes yet?
We saw mercury spectral lines.
Okay, so oh yes, because you use the mercury for the photoelectric effect, right?
Yeah.
Ask her tomorrow, see if she'd be willing to crack out the hydrogen, because we have tubes of all kinds of different gases, including hydrogen, and see if she'll let you crack those out and look at them, because you can really see those lines well. I'll just pull one up here real quick. Hydrogen spectral lines. And let's do an image. There There we go. That's what I want to see. All right, so those are the 4 lines you were talking about, Bradley, right?
Yeah.
And so check out this red one that was at 656.1 nanometers, which I'm pretty sure that's the number we calculated. So this one's coming from the Balmer series. That red one is for when a hydrogen atom goes from the n=3 energy state to the n=2 energy state. When it drops that state, it releases a photon that has this wavelength and it looks red. So think about if you've got a tube of hydrogen gas, think about how many atoms you've got in there, like just tons, right? Tons and tons and tons of atoms. And there are going to be lots of them that are going to be doing that same jump from 3 to 2. They're all going to be producing that color, and so we'll see it. So the 486, that's actually the one that's from 4 to 2. This is the one that's from 5 to 2, and this is the one that's from 6 to 2. The other series, the Lyman and the Passion, those are going to give you wavelengths that are not in the visible interval. So even though they're there, and there's lots of them, right? I mean, you're going to have from 2 to 1 happening just as much as from 3 to 2. We just don't see it. So the answer to why don't we, or why was the Balmer series discovered before the others, is because they could see the Balmer series. It's really easy to see this. You don't need crazy technology to do this, right? All you have to do is excite some hydrogen and then look at it through a diffraction grating. And boom, they show up. So it's things like this that are also like huge evidence that that this quantum view must be accurate, or must be correct, or at least for the most part correct, right? There might be some tweaks that we have to do, but this is what we're going to see in general. So does that kind of answer 26, number 6?
Yeah. Or for me anyway.
So yeah, and I see that Ralph had put it in the chat box, I guess because they're in the visible spectrum. Sorry, I didn't notice that the chat had popped up, but yeah. I want to check something here. Spectral lines, magnetic field. This kind of gets at it. No, that's not what I want. Okay, never mind. I was just curious if maybe I could find something here that was gonna show you something else, but I'm not finding it. Anyway, so yeah, these guys are all the visible ones, and you could actually determine what the different wavelengths are by doing the exact same thing. All you'd have to change in here is the 1.9 electron volts. Make that the other jumps. But you can actually see why the Lyman, for example, there's going to be you're not going to see them. Because check out the difference. That's over 10 electron volts, which means this is going to be 1/5, roughly, what we just calculated. And so just at the minimum, so like the biggest wavelength that you're going to get in the Lyman series is around 130 nanometers, which is way below the visible spectrum. And all the other ones are going to be lower yet because we're dividing by bigger numbers. So those Lymans, they are super ultraviolet. And so never ever see those. And then the problem with the Passion is the opposite direction. Now think about going from 4 to 3, you're dropping 0.7 electron volts. So I mean, let's just even say half of this. Well, half of that makes this double. And now we're talking about things on the order of 1200, 1300 nanometers, which are super far in the infrared. So the Balmer series is just like in the sweet spot. It's in the sweet spot for our eyes to see.
Is this why different telescopes use different wave, like infrared or microwave?
Absolutely. Absolutely. Because you can see different things with the different wavelengths. So yeah, you think about, well, just think about when we send stuff up to Mars, right? We'll get photos that are taken like true color photos, but that's actually kind of on the small side of what they actually do. I think a lot of the real true color photos are taken just for us. So they can show us this picture of what it would look like if you were standing there on Mars to help the human experience. But scientifically, oh no, we get so much more from using X-rays, microwaves, all kinds of other stuff. And yeah, that's why a lot of telescopes are designed to see, for lack of a better word, to see other wavelengths, right? Like we use radio waves. Radio waves are far outside the visible spectrum, but we use radio waves all the time to help us know what's going on.
This is the same sort of thing that they use to like figure out the composition of alien planets too, right?
Mm-hmm.
Like
Absolutely. Yeah. So if and you should always question that stuff, right? When they, I'm a huge fan of the exoplanet exploration. So planets outside of our solar system. And when they find them, they tell us a lot about them. They know their sizes, they know how far away they are from their own suns, all that stuff. But then they also often talk about, yep, and we can tell that this one's atmosphere is made of whatever. And that's exactly what they're doing, Jacob. They're looking at the spectral lines that are coming off, and we know what the spectral lines look like for different gases, for different compounds, and so you can kind of reverse engineer it, right? You get this huge series of spectral lines, and then you can go, oh, okay, so these four are coming from hydrogen. And then
so
we
you
have
could
this
just
other
hold up the
set.
broad spectrum and then like compare it to like a bunch of swatches that have the spectrums that come off of certain gases. That's so cool.
Yeah, totally. Yeah. And so you go, okay, well, so here's hydrogen and then here's an argon. And if we kind of put those overlap and, oh, hey, look, compared to what this is, it matches. So we know that it's hydrogen and argon or whatever. I just threw out argon. I'm trying to think.
Nitrogen's a common one.
Oh, well, I know. Well, on Earth, nitrogen is the most common, right? I'm just trying to imagine an atmosphere that would have like primarily hydrogen and argon. Yeah.
Wouldn't have to deal with it exploding, at least.
Well, I mean, there is that. There is that. All right, so we're good for this one. Make a little more sense, I hope. All right. Okay. So I don't know. This is the kind of thing that definitely gets me excited. Where here was this huge revolution. And we go, hey, it should be quantized, and the next thing you know, we're seeing the evidence of it, and it's explaining so many other things that we've seen. So I want to keep going down this path, talking about how this, how going quantized and still using this wave particle duality leads to kind of a different view of the atom and a view of the atom that's actually very appropriate and explains a lot of what we see. All right, so we're going to go ahead and continue down that path. And so let's actually start talking about the atom as a box, that's holding a particle, and specifically, let's look at an electron. So you may remember last time when we were talking about the Schrodinger equation, we talked about the potential wells. We had potential wells. We started with the infinite potential wells, where we were forced to stay in that box. And then we turned our attention to, well, if it's not infinite, then there's a probability that we are outside, depending upon how close the energy level is to the depth, the potential energy depth. It really determined how likely we were to be on the outside. And then we said, well, what if there's just a barrier? And we saw that you actually can go through barriers, even though your energy isn't as much as necessary for that barrier in a classical way, right? But that was all kind of theoretical. Well, let's look at specifically a hydrogen atom, okay? Because we're going to start with hydrogen because it's super easy. Think about what hydrogen is. You got one proton in the nucleus, and you got one electron that's out here somewhere. It doesn't really get much easier than that, right? So we're going to go ahead and start with hydrogen, but I want you to think about this. That electron is trapped. It's in a potential well. It wants to be, the universe wants it to be, near that proton. Why? What force is actually making it stay?
It's
Electrical.
electromagnetic attraction, right?
Yeah,
Yeah.
it's just the electromagnet. It's the good old E&M force. Because we've got a positive charge, we got a negative charge, they get attracted to each other, right? There is a potential energy between a positive and a negative charge. We already know this, right? I mean, you've known that now for a while. And so that is our potential energy well. Now, if we were to graph it, it's not going to be just like a vertical line, right? Think about the potential energy there. The potential energy is going to die off with radius. The further away it goes, the less potential energy there is, right? So what you would actually see on that graph is something, that does like that as we go farther away. But it does want to stay close to the proton, close to the nucleus. Okay, so it's in a potential energy well. So this is what we're going to do. Let's actually run the numbers on it. Let's take this thing and actually see what it kind of forces if we go with the idea that Bohr had of this electron is orbiting the nucleus. I'm just going to tell you right now, spoiler alert, it doesn't orbit. We're going to see that doesn't quite pan out. But let's just kind of see how that plays out. So we were just talking about the Balmer series, right? And if you look at the Balmer series, I just want to come back to this for a second because it really shows you why Bohr did what he did. So if you want to calculate the wavelengths, Balmer saw that there was a relationship between these things. Now, I want you to realize that this was well before the idea of quantized anything had come about. All Balmer did was he took those wavelengths. So the wavelength for the red, the cyan, those two purples, and tried to find a pattern between the wavelengths. And this is what he found. He found that, so there was some kind of constant R. He had no clue what that R actually meant, but saw that the pattern was that it was always 1/4 minus 1 over n squared. And for those 4, it was for n equals 3, 4, 5, and 6. Now, with the benefit of hindsight that we have, you can look at this and go, oh yeah, totally. This is the jump in the energy levels, right? This is n equal 2, so n equal 3 to 2, 4 to 2, 5 to 2, 6 to 2. And this guy R, that actually holds that baseline, or that comes from that baseline energy, the ground state energy. It's also going to have a C in there because of the fact that this is 1 over lambda, and and the H and all that. But that number, Balmer had no clue where that number came from, but saw that there was just some multiplier. Okay, so he came up with this. Now, this made Bohr go, all right, clearly there's got to be some sort of energy quantization here in an electron, or in an atom, in a hydrogen atom, because these wavelengths are coming from integer numbers. So it really pushed Bohr to go in, all right, there must be some quantumness to a hydrogen atom. So Bohr comes along and goes with what we already know. He says, hey, so the electron orbits right? So the electron is going to orbit the nucleus. And he's like, and it's just going to be in a circle. Kind of going with the same idea of what they knew about orbiting planets and moons and things like that. Yes, they were actually very aware that the orbits were elliptical, not circular at this point. Kepler's laws had been around for a couple hundred years already. But I was like, okay, so we're just going to orbit in a circle. But the other thing that he did is he said, we're going to quantize the angular momentum. Okay, so the magnitude of the angular momentum is going to be quantized. And he figured that's what's going to allow this change in energy, these photons, releasing energy such that it's always, in countable chunks. So think about angular momentum. You guys remember angular momentum? That's a legit question. Do you remember what we're talking about there? Because if not, let's make sure we know.
Yeah, it's the momentum of something traveling in a circular or elliptical path.
Okay, so it's going to be the momentum coming from going in a circle. Do you remember how it's related to regular momentum?
Well, you still need its mass and velocity.
Yeah, you definitely do need its mass and velocity. It also depends on how big of a circle you're going around. Just as an aside, angular momentum, it was R cross P. So big L is your angular momentum, P is your linear momentum. So it was just a cross product of the radial arm and your actual momentum. So here was the thought of Bohr was that, well, okay, obviously when you change momentum, you're changing your energy. And if all we've got is this thing going around in a circle, that's really the only thing you can change is its angular momentum. So that's why he put that into play. He's like, all right, this will make it so that there is a quantized amount of energy, yada, yada, yada. Let's just kind of see what happens. Okay, so now we get to run the numbers. Now we just get to do it. and see what this what the results of this means. All right, so let's just start with the idea of the force. The force that's being applied here, it's electromagnetic, right? So it's going to be K times Q1 times Q2 over R squared, where Q1 and Q2 are the charges of the nucleus and the electron, and then K, that's the it's at 1 over 4 pi epsilon naught, right? Where that's the Boltzmann constant. No, is that the Boltzmann? I think that's the Boltzmann. Whatever. But anyway, that K is it's just the constant. All right. So if we do this for our specific case, we're going to make it a negative force because it's pulling it. We're going to go with 0 being at the center of the nucleus. So it's pulling us towards 0, right? And then the charges for both are both E, charge of the electron. So we're going to get E squared. And then I'll go ahead and put in the K stuff. So it's the 4 pi epsilon naught R squared.
Why is it negative?
Because here's how we're going to do. So here's the nucleus. We're going to go, this is the positive direction. If you've got an electron out here, which way is it? Which way is the electromagnetic force pushing?
Negative.
Yeah, it's moving this direction. Or it's not moving that direction. It's the force is acting in that direction. So if we're going to go with a positive is going away from the nucleus, then the force has to be negative. All right. So there's that. All right. So now let's think about the fact that we're moving in a circle. So from a circle, I'm sure you guys remember that the acceleration, the magnitude of the acceleration is v squared over r. If you don't remember that, that's what we get with centripetal acceleration, v squared over r. So what I'm going to do is I'm going to set this equal to mass times acceleration. So I'm going to put the v squared over r in here. But again, it's going to be negative because the acceleration is pointing centripetally towards the center, which is in the negative direction. All right, so this sort of maroon is the circularness, and the blue is coming from the electromagnetic force. So we can put this all together with if we just solve this guy for r, and going back then to the idea of the angular momentum, let's put that in as well. So angular momentum, L, is not little l, big L, is r cross p, which is going to be r mv times the sine of theta, where if this thing is moving around in a circle, whoops, well, and whatever path it's going, right? So you're going to have the momentum is going to be tangent to the path. And then, actually, let me do this. I'm going to make it so that it's very much not circular path, even though we want it to be a circular path, just to illustrate how this is going. So let's say that's our path. And on here, you're going to have, let's go here. So you're going to have your momentum vector. This is going to be your R vector. And then theta is the angle in between them, which would actually be, in this case, here. Right. So that's what happens when we do cross product. I just jump to the, how this all plays out. But because this is circular, because we're going around in a circle, this means that P and R are always orthogonal. Right? That's a nice thing about moving in a circular path, is that P and R are always orthogonal, which means sine of theta equals 1. So, okay, cool. We know that's equal to 1. So our angular momentum is always just RMV. But now let's go with the quantized angular momentum. And specifically, what he went with was that the magnitude of your angular momentum is equal to n times h slash. So that was the Boltzmann constant over 2 pi. Now, why that? Well, that came from experimental numbers, like to make things match up. He was like, nah, it needs to be that way. So we're going to have n times h slash here. So here's what we can do. We can actually solve this for v, plug that in here to get rid of our velocity, right? V is going to equal n times h slash over r times m. And we'll take this guy, fired in there for v. So the v's are all gone. And then let's solve it for r. Now, I'm not going to do this to you, okay? I'm not going to actually do it. But if you solve for r, you get r is equal to h squared e naught, epsilon naught, over pi m e squared times n squared. So there was a bunch of algebra in there, but like I said, I'm not going to torture you with it. But here's the important thing to notice, is that we've got just some baseline radius. And then the different radii that we can get for that electron are going to be, as we go to higher states, is going to be n squared times that radius. So now not only is energy quantized, but also the radius at which this electron is moving is quantized. So that bit in the green box, we call this Bohr's radius. Because that's the radius of the ground state, and we usually use the letter A for that. So I think I mentioned this. I think I may have mentioned a number for this before when we were just talking about how, Bohr was looking at it going around in a circle. But this is where that number comes from, is from this idea of quantizing the angular momentum. Now, I want you to think about what this would mean if this model were correct. And again, I told you it's not quite correct. But if this model was correct, think about what's going to happen when this electron gets excited, when this hydrogen atom gets excited and that electron gains energy. So it's going to jump quantum levels, right? So it's going to go from n equal 1 to n equal something else. This model is saying, all right, so actually let me turn off my screen so you can see my hands better. So this model is saying, all right, so here's the nucleus. Here is our electron going around. Now, all of a sudden it gets excited. It just immediately jumps out here to a bigger radius. It's orbiting, orbiting, orbiting. Okay, now it's going to give up a photon, and it immediately jumps back in. Okay, now imagine you're a contemporary of Bohr, and you're going to go, whoa, 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 hold the phone here. I'm down with the let's orbit it like a planet. I'm cool with that. But now you're going to tell me that all of a sudden it just changes its location instantaneously because it released a photon or it absorbed a photon? No, because planets don't do that. Right? If we impart some energy onto the Earth, it's not like the Earth's just going to automatically move to another orbit. It could do that over time, right? Like the Earth's orbit could change. Like if we got impacted by something, like let's say a Jupiter-sized planet comes in and hits us. Okay, maybe that's too big because that would probably destroy us.
That would cause all sorts of problems.
Yeah. So, but I mean, yeah. Okay. So the Earth gets hit, and so like a billiard ball, like pool ball, all right, so it moves, and then eventually settles into a new orbit. Sure, I can buy that. This doesn't seem like it fits very well, right? But at least it takes care of the Balmer series stuff, where you go, well, this is why we're only seeing certain energies, certain photons. And also imagine if we could just release our energy a little bit at a time, then, and there was no like ground state. Think about what that would mean in terms of the electron. You give up energy, you keep moving closer and closer and closer until eventually that electron smacks into the proton and the hydrogen atom just goes away. Well, we know that doesn't happen either. So at least this kind of helps with that. All right, so it doesn't sit very well. But now let's just even throw Schrodinger in. Let's look at what happens when we go to the, okay, but what if this is actually a particle that's trapped in a box? All right, well, let me go back to the whiteboard. And I just realized I meant to show you guys one more thing. So hold on here 1 second before I get to the Schrodingers. Talking about this, I want to just show you what happens with energy. If you look at the energy of the electron, so think about the energy in the electron, it's going to be K plus U, right? Your kinetic plus your potential. So the kinetic is going to be 1/2 mv squared. And at least if we go classically, right? And then the potential, if you look at the electric potential, hopefully you guys remember that that's actually very similar to the force. It's a divide by R instead of R squared. So remember this whole like 1/2 mv squared business. Again, we can replace that with our mass and velocity and or like the v that we get over here and do all that kind of stuff. Well, if you do a couple more steps on that, this ends up being minus me to the 4th over 8 epsilon naught squared h squared times 1 over n squared. And again, I'm going to spare you the details of getting to this algebraically. But notice again, there's this sort of like baseline energy. And the other energies we get by plugging in our n. And this ends up being the minus 13.6 electron volts times 1 over n squared.
So energy is going to decrease exponentially as the radius increases, correct? Or energy increases, right?
Okay, so
energy level, I should say.
Okay, so as energy level increases, so as n gets bigger, this number actually gets larger. It goes closer to 0. So it's increasing. So we're increasing our energy. We're also going to see the radius of the orbit increase. Did I catch? Is that what you were asking?
Yeah.
Yeah. Okay. So, yeah. So that's what this model is saying. As we increase n, we're increasing our energy level, and we're also increasing the radius at which the electron is found. All right. Anyway. But now let's throw Schrodinger's equation into the mix and think about what it does. Now, before we get too far into Schrodinger's equation, I do want to talk about quantum numbers because things are a little bit different now. For this, we actually need 3 quantum numbers. And the reason we need 3 is for the 3 dimensions. When we just talked about a quantum, the n quantum number, we were doing kind of everything one-dimensionally, so we get away with this. But now you got to really kind of think about it. Well, in 3D, we're going to need 3 different quantum numbers. And specifically, if you think about spherical coordinate system, remember spherical? We've got r, theta, and phi. We're going to have our quantum numbers based on r, theta, and phi. Instead of x, y, and z, they're going to be r, theta, and phi.
Was that drunk integral man?
Yeah, that is drunk integral man, where phi is tipping over, and then theta is spinning around, and then r was the height of integration man. Yep. Okay, so r, that's your distance away from the nucleus. And so we actually already have a number that's going to work for that. And that's that guy n that we've been talking about. Because remember how n, as we increase n, we're increasing our distance away from the nucleus. So n really does sort of account for changes in r. Now n, we name this thing the principal quantum number. And that name makes sense, right? Because principal, primary, the important one, right? This is the principal quantum number. And really what it does is its energy level, right? If you think about it, the main thing it does is it determines the energy level. It also then leads to where we're located, but that's really its primary thing, is determining the energy level. Okay, now for theta, so for the theta direction, which is now the spinning around in a circle. So it's the same theta that you're used to from polar. We use the letter L. Now L, I call this a different thing than the book calls it because I learned it differently, but I call this the orbital quantum number because it's all about being in the orbit, right? The orbit, you're going around in a circle. Your thetas are going from 0 to 2 pi. So this is your orbital quantum number. The book, if you look at the book, they call it the angular momentum orbital quantum number. And I think that the reason they do that is because it really highlights what it affects. It affects the angular momentum. All right, so like N determines your energy level. L, this is going to determine your orbital angular momentum. So the big L, right? It's going to affect the big L. All right. So then for phi, that's the drunkenness of integral man, right? So that 0 is vertical. And then as we go down to horizontal, that's pi over 2. And then you can go all the way down. Oh, got caught by the earphones. You can go down to pi, right? So from 0 to pi over 2 to pi. So this one, I'm going to divert a little bit from their notation. In the book, they're going to show this as M. I don't like that because whenever I see M, I think mass. And so what I'm going to do is I'm going to put M and then a little L subscript. Because this is also something that's determined by your angular momentum. So the little L just reminds us that these kind of are tied together. And the way I learn this, the name of this thing, and why there's M, is that this is the orbital, that's the L bit, magnetic, that's the L piece, quantum number. So that's how I'm going to reference it. I'll explain why it's called the orbital magnetic quantum number. But that's why the M comes in, is because it's magnetic. I just don't want to write M because I'm going to think of that as mass otherwise. So the book, of course, calls this the angular momentum projection quantum number. Okay. So we'll talk about why it's called what it is. But what it really affects is the tilt of the angular momentum. Remember, angular momentum is a vector, so this ML is going to determine how much it tilts. All right, so those are the 3 quantum numbers that we're going to use when we're talking 3-dimensionally. So from here on out, when we're talking about atoms, we're going to use all of these. We're going to see that there are actually more quantum numbers as well, but these are the 3 we're going to talk about just now. So N, again, we already know what N is. N, well, not M. N takes on the values 1, 2, 3, 4, 5, and so on, right? So the lowest N we can have is 1. But then we can just keep counting up as much as we want. Now, the L, there are restrictions on what the L value can be. It can actually be 0. That's the lowest it can be. But again, you can just start counting up with it. But there is going to be a maximum that it can have, which is going to be N minus 1. So basically, you give me your principal quantum number. You tell me the energy state that we're in. That's going to limit my options for L. But L can be any of these numbers for a given N. So for example, if N is 3, then we have 3 choices for L. L can be 2, 1, or 0. So all of those are possible. Okay, so that just means then if we're looking at, well, this is determining our angular orbital momentum. As we increase our energy level, we're going to have more options for how much angular momentum we have. If N is 1, we're actually forced to L equals 0. That's the only option. And so if L is equal to 0, then you know that there's only one orbital angular momentum that we can have. All right, so that's L, and then M, or in my case, M sub L, it actually can also take on negative numbers. So it can be 0, plus or minus 1, plus or minus 2, and so on. But the most it can be is plus or minus L. We'll see in a little bit why there are some restrictions here, why you can't just have anything for these. All right, so for every energy level N, there are going to be a bunch of options for L, which are going to have a corresponding bunch of options for M sub L. So there are lots of different possible states for any one atom. All right, well, let's talk a little bit about L and M sub L, what they do, and why we know about them and all that. So the orbital quantum number made sense that it needed to be there. And by looking at things experimentally, it was determined that your angular momentum big L is determined by little l in this way. Okay, so this is the magnitude of L, so it's not the vector itself, but the magnitude, it's actually equal to the square root of L times L plus 1, and then that's all times H slash. So this isn't obvious at all, but by looking experimentally and kind of running the numbers and setting this up, they found that the magnitude of the orbital angular momentum was determined by this formula. So think about this then, as we increase N, we're increasing our options for L, which is giving us lots of other options, or for little l, lots of different options for how much angular momentum we have. But it should kind of make sense that the more energetic we are, the higher our N, that it's possible to have greater angular momentum, which we definitely do by this formula. Now, for you chemistry types, in chemistry, we use letters to represent these different states. And so when L is equal to 0, that's your S. When L is equal to 1, that's your P. L equals 2, that's your D, and so on. And if I recall correctly, the next one's F, right? S, P, D, F. And then I think it just goes in alphabetical order, I think. It's been a long time since I've taken chemistry. So back in the day, when you saw things like 1s, what that was really telling you, the 1 was your principal quantum number, and then the S was telling you, oh, we're in the L equals 0. So I don't know if you remember this, but you only ever saw 1s. You never saw 1p, 1d, 1f. It was only 1s because 0 is the only option when you're at n equal 1. When we get up to 2, you can have 2p, or you can have 2s. And you probably saw both of those, right? And then similarly, if you go up to 3, you can have 3d or 3p or 3s, and so on down the line. All right, so that's what the L is. It was all just a measure of angular momentum. So then M sub L came about because of a kind of funky thing that happened when they were playing with hydrogen and looking at the spectral lines. And they realized that if the hydrogen was in a magnetic field, they were getting extra lines. So think about what that means. If we now start getting other lines, that means there are some other energy drops. And specifically, these things were coming in triplets. So remember how we saw the red band? Well, you apply a magnetic field and you don't just see a red band, you see 3 that are all really kind of close together in that same red area. And that was called the Zeeman effect because it was named after this guy by the name of Zeeman. And they started looking at it and thinking, okay, so what would describe that? What would explain that? Well, they realized they need another quantum number. And that's why this is the magnetic quantum number, because it came from looking at this with a magnetic field applied. And what they realized was that what was going on there was that the orbital angular momentum had different orientation sometimes, and that different orientation meant that when they applied an electric field to it, they got different results. Because as we know, your vector orientation is super important when you're talking about electromagnetic fields. All right, so here's how this breaks down. If we are just looking at, here are axes, so think of this as your nucleus or whatever. But let's say here's our L. Okay, so this is our vector L. This is our angular momentum vector. What they realized was that since the orientation mattered, what they really needed to look at was the component of this thing. And so I'm going to call this L sub Z. We think of the Z axis, it's the one that's going straight up. And they realized that that LZ was what was being quantized. And so the magnitude of LZ was actually equal to this M sub L times H slash. So that meant that there were just some very specific orientations for our L. L can't be pointing in any old direction. There are only going to be some very specific directions depending upon their Z component, which was given by this. Now, that's why the book calls it the angular momentum projection quantum number, because it's the projection of the angular momentum vector onto the Z axis. But again, you can see what I mean by it affects, or it helps determine the tilt of the angular momentum. So think about the options that we have for M sub L. I told you it can be 0, plus or minus 1, plus or minus 2, all the way out to plus or minus L. And I want you to see why that is. All right, so remember what our L's magnitude was. It was this L times L plus 1 in the square root times H slash. So the H slashes don't matter. You can kind of just ignore those. But think about what this means if, say, M sub L is 0. If M sub L is 0, that means that your Z component of the angular momentum is 0, which means L points this way. So this is ML equaling 0. Okay, so then we start increasing our ML. So ML equals 1 means there's now going to be some chunk of, let's just say that that's H slash. And so now our L vector is going to point there. So this would be ML equals 1. Let's say we go to 2. So then this would be ML equals 2 and so on. But eventually we're going to get to the point where if we went too far, like I think that's going to happen here. If I tried to go to 3, it's saying I need to have a Z component of that length and my vectors aren't that long. And if you look at this, the square root of L squared plus L is bigger than the square root of L squared by just a little bit. And that's why we always have to be, and it's under the square root of L plus 1 squared. So this thing right here is always between L and L plus 1. So if we try to go up to L plus 1, it's too big and we go too far. So that's why that's capped. And then the minuses are fine because then we're pointing in the other direction. So this would be -1, -2, and so on. All right, so this quantum number deals with tilt, with phi. L deals with going around in a circle, the theta. And n is how far away we are, so our r. But the one other thing that we can do with this is we can actually calculate the tilt. So if we call that guy theta, what we know is that the cosine of theta is going to equal the magnitude of LZ over the magnitude of L, just from trig, right? Which is going to be ML times H slash over the square root of L times L plus 1 times H slash. So the different possible angles we can get, different possible tilts, are going to be given by the inverse cosine of ML over the square root of L times L plus 1. All right, so yay. There's our third quantum number, but now we got 3. So this all came from the idea of we're going around in an orbit. If we're going around in an orbit, all this has to be true. And by looking at it experimentally, we saw that, yeah, this definitely seems to hold. Okay, but remember I told you we were going to look at Schrodinger's equation, and we still haven't talked about that. But I just want you to think for a second about Schrodinger's equation and think about what it's going to do. Like, we haven't even talked about the waveness of electrons yet, right? Like, all of this was totally just, we're looking at going around in a circle. Okay, well, let's talk for a second about waveness. So let's introduce that to the mix. So Bohr comes along, we got this electron cruising around like a planet. Yay, cool. But now we go, well, wait a minute. That electron actually is also a wave. So it's going to have wave-like properties. And what did we see last time? That's going to make it awfully hard for us to say that this thing is moving around in a circle. That has to do with waveness. I can think of 2 things that I'm trying to push you towards. How about this? Think about psi, the wave function. What does psi tell you? What do we use psi for?
Isn't it to show position?
So we did use it to help us talk about where it would be located. Maybe better is like, what does psi squared tell us? I was thinking that you guys would probably remember, but maybe not. The likelihood of you remembering is very low.
Isn't psi squared the half of a wavelength in which it moved?
It is not half the wavelength, no.
It was a probability, right?
Yeah, it was a probability. I was trying to drop you guys hints with it. You're probably not going to remember. The likelihood is low. Look, I'm trying to entertain myself. All right. Now, so psi squared gives us probability. So think about what that meant. Like when we talk about this as a wave, we don't know exactly where it is. We know probably where it is, or the likelihood that it's in a certain spot or not. But as soon as we go to this waveness, we're going to talk about locations as probable locations. Even more, now that I'm kind of going that direction, kind of where I was going with really the issue is Heisenberg. Remember Heisenberg's uncertainty principle? Says that we never actually truly know where something is. So trying to say that the electron is going to be going in an orbit around the nucleus, if we start throwing this waveness in, that's going to fall apart. Because it can't. Because otherwise we'd know exactly where it is. Right? At least we'd know where it is radially, which is just as big of a problem with Heisenberg's uncertainty principle. Okay, so, but let's do it. Let's look at what Schrodinger's equation has to say regarding the location of this electron, or the wave function of the electron, and then we'll look at the probabilities and see what that does. Now, before you go, well, shit, we're screwed. We're not. We're definitely not, because these effects that were being seen that got explained by Bohr's model are still out there, and we're still going to use these quantum numbers. It's just they don't quite mean exactly what we think they mean. Like when I talked about the angle for the angular momentum. Well, okay, yeah, that angle exists, but it's meaningless. It doesn't mean that, oh, that's an angle that's kind of relative to the circle in which this is orbiting. No.
And that's solely just because of the fact we don't know.
Yeah, because we don't know exactly where they are. All right, well, let's do it. Let's go take a look at what Schrodinger's has to say about this. Okay, so
I have a quick
yeah,
question.
Yeah, go for it, Bradley.
What came first, the Bohr model or Schrodinger?
Bohr.
Okay.
Yeah, Bohr's model came first. All right, now I'm going to do you a favor, another favor here. Hold on a second here. Sorry. I'm going to do you another favor. I'm not going to show you the derivation where this comes from. Okay, I'm not going to do all the numbers on it because it's pretty gnarly. So instead, let me just kind of show you what it is. Now, we're going to apply this. Let me do Schrodinger. Again, this is going to be time independent. And we're going to do this one-dimensionally. Okay, so we're going to do it 1D with R as our position. going with the idea that this is going to be symmetric in all three directions, right? Like if we're talking about 3D and all we're talking about is where an electron is going to be located, it shouldn't matter which direction we're radiating out. We should expect to see the same thing everywhere. Okay, so this is going to be, R is going to take the place of X, but it's still going to be time independent. Now, in terms of the U, we're going to use the potential energy from E and M. All right, so that's going to be the minus K Q1 Q2 over R. So that's what's going to go in for our U. In terms of the energy, well, we calculated the energy. I showed you what the energy was according to this model, and so we'll put that in. But long story short, after doing all of that good stuff, what we get for our wave function in terms of R is 1 over the square root of pi times a to the 3/2 times e to the minus RA. All right, so this guy A, it's that same A that we saw before, which is Bohr's radius. I'm kind of chuckling because my dog just came in, grabbed her bed and started shaking it around in her mouth. That's her, you're not paying attention to me move. So that just made me laugh. Anyway, sorry. So A is that Bohr's radius. It's that same number that we calculated when we used Bohr's model and kind of did the whole, let's look at F equals MA and blah, blah, blah. The other thing that is very important for you to realize is that this is specific to n equals 1. All right, so this is for ground state. And you can probably see why that matters. What is changing state going to do? Like if I increase my n to some other state, why is that going to affect our result from Schrodinger's equation?
Well, because it's in terms of R.
Well, yeah, so it is in terms of R, and we've already seen that from Bohr's classical kind of approach, classical / quantum approach. We're going to get different R's. But go back to the equation itself. Think about Schrodinger's equation. It had psi double prime, some stuff out here, right? Don't worry about that stuff, but it was stuff times psi double prime plus u times psi equals e times psi. What does increased n change in here?
R E on the right hand side.
Yeah, there's like a huge change in this. And as soon as we change that, we should expect that we get different solution. But also there is a change in the U because our R's are being affected, like you said originally, Bradley, right? So we increase our N while we're still using the same form of the equation. The structure or the actual numbers changes a bit, which means we're going to get a different psi. Anyway, I just wanted to point that out because it's not like there's the one psi for every hydrogen atom in the world. This psi is for a hydrogen atom in the ground state. If we, and you can do it for n equal 2 and n equal 3 and n equal 4, and it has been done for different n's. But it changes what we see.
I have a quick question.
Sure.
So since there are different possibilities for psi in this case, will they be like totally different, or will they form a basis?
They are going to be well, I don't want to say totally different, but they are very different.
Okay.
And when we start getting into like even more complex atoms, I mean, even if you just go to helium, where you've got 2 electrons. The 2 electrons affect each other, and then it gets crazy. So it's not like you can use the one to create the others, which is I kind of think what you were getting at when you say forms a basis.
Yeah, because I was thinking about this more in a differential equation sense, and like maybe finding like a spanning set of solutions. But
Well,
if they're completely different, then that might not work.
but just think about it though. When we found a spanning set, that was for the specific differential equation. And if you were to, and it formed a basis for solutions to that differential equation, where if you change the numbers on it, now we're going to get a different basis because the solution space is a completely different group of things. Right? Does that make sense? That when we form the basis, it's the basis for that differential equation and its solutions.
Yeah, that makes sense.
So there is going to be a basis for Schrodinger's equation when it's the ground state of hydrogen. But there's also going to be a basis for the solution set to the n = 2 state of Schrodinger's equation in a hydrogen atom. And what's even worse is like if we go to n = 2, there's more than just one case when n = 2. Because remember those other quantum numbers? Those other quantum numbers can change, and they're going to change the energy, which then changes the differential equation, right? So for every combination of N, L, and ML, for every combination of those quantum numbers, you're going to get a different solution. So you can see how messy this gets, right? The fact that we're just looking at the ground state is like super easy, because this means n = 1, L = 0, and ML = 0. And like I was saying, if I just bump this up and we go to the, okay, well, what about the n = 2 state? Well, here are different possibilities you can get with n = 2. We can have n = 2, L = 0, and ML = 0. We can get n = 2, L = 1. Well, if L = 1, then ML can equal 0, or ML can equal 1, or ML can equal -1. Right? So if we go to n = 2, there are actually 4 different Schrodinger equations with 4 different solutions for psi. And that's just n = 2. I mean, imagine we go to n = 3. Oh, good Lord.
Would it be a square? Would it be 9?
That's a good question. I wonder if you could figure that out.
I'm sure I could if I played with it.
It is going to be 9. Because check this out. Every time you bump up an L, so like at L = 0, there was 1 choice for ML. For L = 1, there are 3 choices, because you have the 0 and plus or minus L. So if L is 2, you're going to get 5 choices for ML, and then 7, and then 9, and then 11, and so on. And when you add consecutive odd numbers, you do get perfect squares. So yeah, I won't hold that over you. So if we're at n = 3, there are 9 of them. N = 4, there's 16. N = 5, there are going to be 25 different solutions. So every one of them is specific to the one scenario. And for us, for just the simple ground state, this is what it looks like. Okay, well, now that we see what the psi is, let's talk about probabilities. So we're going to do probability by looking at psi squared, but we have to adjust it ever so slightly because of the fact that this is three-dimensional. Because now when we talk about the probability of being in a location, this is going to be the probability of being a certain distance away, we have to account for the fact that that distance away is in all different directions. So I'm going to make this a PRDR. It's going to be the psi squared, but now we have to go to 3D, which means it has to be a dV, psi squared dV, where before it was psi squared dx. Right? So it's going to be a psi squared dV. Well, this isn't that big of a deal. Let's just go ahead and put in our psi squared. So we square this thing. You're going to get 1 over pi a cubed times e to the minus 2r over a. That's your psi squared. And then dV, well, it's going to be 4 pi r squared dr. Take your volume, 4/3 pi r cubed, differentiate it, you get 4 pi r squared dr. Or you can also think of it as that's the surface area times the thickness. Either way. So we put that all together, and you get 4r squared over a cubed times e to the minus 2r over a dr. So this is your probability being at any one location. So this is your PDF, this guy right there. So let's draw a graph of it, so you can see what it looks like. And totally, you can just use your graphing calculator to do this, but you get something that looks like this. So on this graph, of course, this is R, and this is your probability. And you notice that there is a peak right here. So if you differentiate, find that max, right? Find that critical point, guess where it is? It's at Bohr's radius. Woohoo. Okay, so even when we throw Schrodinger now in and go, okay, well, it's a wave, so we don't really know, we still see that its most probable location is the location that was predicted by the model of the planetary model of Bohr. So think about how happy this just made everybody. Maybe not you guys, but think like back in the physics world. Because now we go, all right, well, we don't really know where it is, but it's probably going to be where we think it is. Oh my God, that's nice. That means that Bohr's work doesn't have to get thrown out. It still is valid. It just means we're not 100% sure that it's right there, but it's most likely there. So this leads to the idea of the orbitals, of the electron clouds or whatever. So like when we are actually talking about an electron in this simple hydrogen world, okay, we don't know exactly where it is, so there's some fuzziness to it, but it's most likely at this Bohr's radius. Let me show you at least what the graph of the n equal 2, L equals 0 case looks like. If we look at that one, it's got a graph that kind of looks like this. And so there's still a most likely location, but now there's a second location where we might see this.
Would that second location be Bohr's radius?
All right, so remember how in the model for Bohr, the radius was dependent upon your n? ish, sort of, maybe. Go
Yeah.
back and look at your notes.
Yeah.
Okay, well, that's why we're starting to see multiple possible locations, because those correspond to the different multiples of Bohr's radius. So, kind of crazy. But when you get up to this n equal 2, and then you say you go to L equal 1, now it's not spherical. Now, what you're going to see is I'm not very good at drawing it, but kind of the hourglass shape. Or I guess, what do you guys call that? The peanut shape, I think, in chemistry, to remind you that it's a P, right? So S was spherical, and then P is peanut shaped. When you get to the n equal 2, L equal 1, you start getting this sort of solution, so that it's not spherical anymore. It's still 3D, but it has got some symmetry, but it's not spherical. All right, well, you bump it up, it gets crazier and crazier and crazier. And I forget, what is the D is the one that kind of looks like a diamond D shape. Is that right? I don't know. Again, I'm going off of like 30 plus years ago chemistry class. So, but it all of it comes from Schrodinger's equation. It all comes from actually solving that differential equation for the different energy. All right, so, dude, weird, totally weird. But at the same time, it's beautiful. It's actually beautiful in its simplicity. I say that it's simple. I know mathematically it's not, but think about just the idea behind it. It's not a super complicated idea. And yet every time we try to, we add a little bit more complexity, it still lines up with what we see in the real world. So I guess the moral of the story as of right now is there's more than one quantum number. We looked at it from a traditional classical standpoint combined with quantum, that then we throw in the wave nature, and oh my God, it explains everything that we see. So I think we're going to stop here. This is a good place to end today. But what we're going to do next week on Tuesday is just, we're going to keep running with this. I'm going to show you another quantum number, and then we'll start talking about what happens when our atoms get a little bit bigger, why the periodic table is laid out the way that it is, and then we're going to start wandering into the nucleus. Talk about the structure inside the nucleus of the atom. So that's where we're heading. All right. So with that, oh yeah, one more thing. I just did put in a homework for chapter 7, I think. That's due next week. So that's in there, so you can start playing around a little bit with that, with Schrodinger's equation stuff. All right. So with that, I'm going to stop our recording and wish you all a very wonderful weekend.